All right. So what we'll do today is a revisit of what we talked about last Thursday, and I'm going to give you some examples. Okay, so hopefully the concrete examples will help you kind of connect the concepts that we talked about last week. So we're going to start with a number, okay, so that we can convert or figure out the value of the number. And let me start a text editor so I can kind of keep track of the number that we are looking at. Okay, so go to accessories, mousepad. There we go. And then make a new window. There we go. All right. So I will leave the formula open. All right. Are you guys ready? Okay. So we are looking at an example, and I will use a base 7 number. We'll choose 416 in base 7 for this example. So we talked about how a number is not the same thing as a value. A number is a representation of a value. So now we have a number called 416 in base 7, and we want to figure out what is the actual value represented by this number. The formula that is useful is the one that you see on the HTML document. So now we just have to figure out, okay, what kind of D of I are we talking about? What is the B, and what about the I? What is I doing? Okay, so now we look at the number. Okay, so this part I'm going to use the whiteboard just because it's a lot easier for me to write this on the whiteboard. And since I'm describing what is on the whiteboard, even people who are not currently in class, they can either look, ask for one of you, for the notes, or they can just listen to what I'm doing. All right, so we are writing 416 like that. So the first question is, which one is D of 0? Which one is digit 0? What does digit 0 do? Yes, 6. That is correct. So 6 is our D0 because it is digit 0. Digit 0 is the digit that tells us the quantity of whatever base raised to the power of 0. That's why it's called digit 0. So that means here the 1, which is the second digit from the right, is D1, and then the 4 is D2. So are we okay so far in terms of understanding how we number the digits? Okay, so now that we have these, what about B? Okay, because in the formula, B is the base that we raise to a certain power based on I. So what is B in this case? It is 7. Okay, we're dealing with a base 7 number, so B is 7. All right, so given these, can we figure out V? All right, so let's go ahead and write out V. And V is, this part I can actually do in the editor, so we can just type it out. So in this case, V is going to be, um, now what about D negative 1? D of negative 1 has to exist because otherwise this sigma notation would not make any sense. Well, it does exist, except it is a, okay, let's take a look at 416 and we'll kind of write it out in a very stupid way, and then we'll figure out why all of those other digits are actually here, but it doesn't really matter. Can I do something like this? About another one. We can extend all the zeros to the right hand side, right? Can I put a 0 here? Would that change? Okay, why would you turn your head? Why would that change the value? It does not change the value. Can I put another 0 here? Yeah, I can extend on the left-hand side and pad as many zeros as I want without changing the value that I'm representing. So why don't I usually just write a bazillion zeros followed by the significant digits and then followed by a bazillion, decimal zeros, zeros, on the right-hand side of the decimal point? Because it's a waste of time. That's why. Does that make sense? Okay. Now, most of you are lucky that you don't have to do your own taxes because you're not making enough money yet. Okay. But that will change, hopefully, in about a few years. So the tax form is designed for everybody, right? So they have a certain number of digits for your salary. So for a billionaire, they're going to have to fill in a lot of digits. Now, obviously, they're not going to do their own tax forms, but since you have to do your own tax forms, do you have to write zeros until you get to some non-zero digits like what I just did? No. If it's okay with the IRS, I think it's okay with us. It is federally approved. Yes. All right. So now we can now go back to the V and we just say that, okay, since there are only a few digits that are not zeros, so now we just go like, okay, this is the D of 0 times 7, which is our base, raised to the power 0, plus D of 1 times 7 to the raised to the power of 1, plus D of 2 times 7 to the power of 2. And since we already know the values of D0, D1, and D2, so now we just kind of put those things in, and I'm going to do the super lazy thing by copying, pasting, and modifying. Typically not a good thing when you're programming, but we are not. I'm just using this as an example. Yep. Oh, 6. Yep, you're correct. This is a 6, this is a 1, and that is a 4. So now it's just a matter of doing arithmetics. So I hope you guys can do this in your head without using a calculator. So this would be 6 times 1 plus 1 times 7. So far, it's super easy. And then 4 times 49, also pretty easy. So now we have what? 6 plus 7 plus 200 and, oh, 196. Now, how can I do this mental math, quote unquote, so quickly? That's one way, but I did a cheap trick on it. I just calculated 4 times 50 minus 4. Yes. So in math, in algebra, which rule did I use to do that little shortcut? Distributive law. Yep. Because in my mind, I rewrote 49 as 50 minus 1, and then I do the distribution. So now I have 7 times, no, 4 times 50, which is easy to do, and then we have 4 times 1, also super easy to do. 200 minus 4, also super easy to do. Okay, so those are the kind of little mental trick that I can use when I'm doing arithmetics by hand. Did you guys? I know some of you know that trick already, okay? But those are the kind of things that is being lost, okay? I've read a lot of articles that talk about, how I guess high school students now do not know how to do division, even with a piece of paper. They don't know how to do it. It's not a matter of, yeah, it's going to take me a little bit of time. Nope, they just did not know how to do it. All right. So we just have to finish this calculation. So we have 203 plus 6, so we have 209, I believe. Okay, let me double check to make sure it's right. So 13, yep, I think everything is good here. All right, so are we good so far? I just illustrated an example of how to apply the formula, this one, to go from a particular number in base 7, which is a really strange base that you're not going to use outside of this classroom, into the value, which is natively represented in base 10. Are we good? All right. So there's one more equation or one more formula that is particularly useful in this particular note here. And if you have read the notes and have identified those equations and have figured out how they work, good job. Okay. On the other hand, if you have not done so, well, today's lecture is a kind of quick touch on those formula and how they work. So the second one is the one that you see on the left-hand side of the editor. It says d of I equals to the floor of v divided by b to the power of I mod b. Okay, so now we're going to take the base 10 number, which is 209, and try to reverse it back to d0, d1, and d2, just to double check our math, because we should get back the original digits. Does that make sense? Okay, I see some nods. Okay, so we're going to go do the calculation, and I'm going to do this on the whiteboard just because it's easier to do this kind of stuff on the whiteboard. And where's my pen? There we go. All right, so we are going to have three cases. Okay, what is B again? What base are we converting back into? 7. Okay, because otherwise I cannot tell whether I got it right the first time or not. So we're going to convert it back to base 7. So B is 7. What is V? What is the value that I want to convert into base 7? 209. Very good. So we say V equals to 209. And now we just have three cases for I, because we have digit 0, we got digit 1, we got digit 2, right? So when I equals to 0, we'll work with that case first. So the formula is going to say, okay, this is what we need to calculate. We have 209 divided by b, which is 7, to the power of I, which is 0. Take the floor of that whole thing, and then we just do a mod with 7. Okay, so what is that going to be? 7 to the power of 0 is 1, which means the division is trivial. Okay, there's nothing to do here. 209 divided by 7, so you can do a long division. Okay, so with something that simple, I can just do it like the abbreviated version of a long division. So we divide it by 7. There are 2 over here, 69. 69 divided by 7 is going to be a 9, I think, with a remainder of, so 9 times 7 is 63, so it has a remainder of 6. Is that okay? So that means, what does it mean? It means d of 0 is 6. Is that okay? All right. What happens when I equals 1? Plug in the whole thing again. 209 divided by 7 to the power of 1. Take the floor and then mod it with 7 again. So this time I can, actually, I got it wrong. No, no, this is fine. Okay, never mind. Okay, I just got a brain fart. Okay, yeah, we're good here. Okay, so this time we have to get the quotient of the division, which we got here already. Okay, so that means the 29 is this portion. So now we take 29 and then divide it by 7, and we want to get both the quotient as well as the remainder. 29 divided by 7 is a 4, because 4 times 7 is 28, with a remainder of 1. Does that make any sense? The remainder is the digit. So that means d of 1 is 1. So now we can move on to the last one, which is I equaling to 2. So technically, we are doing this, okay? 209 divided by 7 cubed, or squared, sorry, and then mod it with 7. But guess what, this number is? This number is just 4. So let's just say that you guys are not convinced, okay? That cannot be 4. So we're going to do the long division. Okay, so this time we're going to do the super long division of 209 divided by 49. Okay, well, 0 here, 0 here, and I believe that there's a 4 over here. So 4 times this, we already came to that conclusion earlier, is 196. You divide 209, sorry, you subtract 196 from 209, you get a 3 over here, and there's a 1 over here. So this is the remainder, um, which we don't care about. This is the quotient. So the quotient is basically the floor of 209 divided by 7 squared. So now we have to mod, so we now have to calculate 4 mod 7. 4 mod 7 is just 4 because 4 is less than 7. So that's why that one is pretty easy to calculate. So D of 2 is 4. So are you convinced that we are getting back the original base 7 number? And do you understand how to apply the formula that is displayed on the screen? We're good. I got some confirmation. Okay, so are we all good? All right. Yes. The division, as the value. Oh, you can work that way. It actually works down to the decimal part of a number representation. Okay. Yep. Yep. That's how we can calculate the digits to the right hand side of the decimal point. That is correct. In fact, I can give you guys one more example just so that we can see how that part works. Would that be good? Okay. So since some of you have your notes in front of you, can you remember um, the number that we worked with on last Thursday for the base 2 conversion? There should be a number that has a decimal point, but I cannot remember the value. Hmm? 46.125. Okay. So is it 46? 46. Okay. 46. Okay. So let me just kind of go back to the base 2 representation first so that we can double check our math in just a little bit. Okay, so I'm doing the conversion in my head right now, but I'm using the screen as a piece of paper. This is 32 plus 8 plus 4 plus 2 plus 0.125. So now we know that this is 1, 0, 1, 1, 1, 0. 0.001 in base 2. Okay, so is that kind of the number that we got? Okay, very good. All right, so this is just an example that we have already gone through last Thursday. So what we are doing today is we are isolating one of the digits of the base 2 representation just so that we can see whether the equation is going to work on the right hand side of the decimal point. So I'll let you guys choose which of the digit on the right hand side of the decimal point we want to work on in this case. This is digit -1, this is digit -2, this is digit -3. Which one do you want me to work on? Say again? -3? Okay, so we're gonna change the equation or change the values a little bit, but we're gonna work on that. Okay, so, all right, so we'll go ahead and work this out. Okay. So this time our b is going to be 2 because we are converting to base 2. And our v is the number that we just kind of talked about, which is 46.125. Okay, are we good so far? And we're only working out one single digit, okay? Because if you see how this works, the other digits should be pretty easy to do. So I is -3 in this case because we're trying to figure out what is digit -3. So now we just have to do the math, okay? The math is 46.125, which is our v, divided by 2 to the power of -3, because -3 is our I, 2 is our base b. Take the floor of this division, and then whatever this thing comes out with, the floor of that is going to be modded with 2, okay? And that would be our digit -3, which should be a 1. Okay, so we'll go ahead and do this math. Okay, so we have 46.125 divided by basically 0.125. So there are a few ways to look at this. You can actually do the division with a calculator, but you can also just go like, oh, this is really just the same thing as 46.125 times 8. So we are just going to do this one here. Um, so on the decimal side, 8 times 125 is exactly 1. So we have 1 from there. And then 46, 6 times 8 is 48. And then we have 4 times 8, which is 32. But since it is 40 times 8, we have 320. So I know the answer already just by looking at this whole number here, but we're going to finish the addition and then we do the mod and do all kinds of good stuff like that. So this is a 9, this is a 6, this is a 3. So that is representing the floor of the division. So now we take 369 and mod it with 2, and I don't really have to do any actual math in this case because of the base 10 trick. So this is just 1. So that confirms, that digit -3 is in fact a 1. So it works on the non-negative powers of 2. It also works on the negative powers of 2, or whatever digit is on the right-hand side of the decimal point. Are we still doing okay so far? We good? All right. So I really hate to say put it this way, but it literally is plug and play. Okay, it's just plug and play. Identify what is your I, which is which digit we are talking about. Identify your V, which is the value that we need to convert back into a different base this time. And also identify your base, which is, well, guess what? The base of the number that you need to come up with. So this is going to be in today's lab. Um, which means, understanding this is actually kind of important so that you can get the lab done as early as possible so I can get out as early as possible too. All right. There has to be something in it, right, for me to kind of get you guys, through this as quickly as possible. All right. So that pretty much concludes this entire reading module. So this entire reading module ends, with some, kind of AI generated question. We can go ahead and, kind of work on some of these. We'll just do the hard ones. Why bother with the easy one? Okay, we'll choose the last one of the hard ones. Describe the process of converting a base 10 number to a base B number. Well, you just have to apply the that formula, to all the digits until the number is accounted for. So, let's check the answer. Let's check the answer here. Keep track of the remainders. Okay, so that's a different trick, but that works too. All right. Have I ever shown you guys, how to make use? I think I did. How to make use of Gemini to come up with a quiz so that you can kind of have the AI to quiz yourselves to see whether you're understanding the material. So there you go. Okay, I think that's a pretty useful study technique, not only for this class. I think your calculus classes probably will be fine too with AI. AI can't do everything, but there's nothing that you study at a 2-year community college that AI cannot handle. Possibly 4-year too, at least by the time you get to the 4-year college, 4-year university. So I highly encourage you guys to make use of those tools that are now available to you to help you study. Okay, those are all the tools that I did not have access to when I was a college student. Cool. So that means we are ready to move on. Okay, so we are ready to move on. And if you are following the lectures and you go like, okay, we are almost done with the previous module, you can go ahead and start to read the next one. Okay, do not wait for me to say, oh, we are moving on to the next one. You can always just kind of follow the order of the modules and just kind of move on to the next one as soon as one is almost done. Okay, it is always important to read ahead a little bit just so that you understand what we are going to be talking about. So now we're going to talk about binary addition and subtraction. So let's go ahead and click on that one. But you can also see why it is super important to get the earlier concepts cleared, because for people who do not understand the conversion process of or how a number is representing a value, this will be very difficult to understand. Okay, so that's why it is always important to make sure that you conceptually you are understanding all the material before a certain class. Okay, that's always important. All right, so what this module does is it will start with something that you are familiar with, which is base 10 addition. So if I were to just to read my own notes here, I'm just going to start with this, okay? So this is basically saying I'm adding two numbers. 752 is X, 249 is Y, and I'm just adding those two, and the answer is a little awkward, okay? Because if you look at the answer, it is 001 with an overall carry of 1. That overall carry of 1 is if I need to number the digit, which number would that be? What is the position of the overall carry? Let me use a mouse pointer to point to the one that I'm talking about this one over here. Which digit would that be? It's digit 3. So digit 3 tells us the quantity of, in this case, is base 10. So it would be the number of 10 to the 3, which is also 1,000, right? So that means the overall carry is a 1. That means we have 1,000 coming from this overall carry, which is not considered a part of the sum. There's a reason why that is the case. And then we add the 1 to it, which is 1,001. Okay. So the question to you is, if you add 752 to 249, do we get 1,001? Exactly. Okay, it is 1001. So the reason why the sum is not 1001, but instead it is just a 1, but with an overall carry of 1, is because when you use a machine to perform the calculation, x, y, and the sum, they must have the same number of digits. Okay, let me say that one more time. Because x, y, which are the numbers that you're adding, they come from some kind of hardware inside the processor, which has a fixed width. Okay, it can only store a fixed number of digits. The sum also has to go back to one of those things. So that means you have the same restriction for the sum. It must have the same number of digits as the value that you're adding. Go ahead. Nope, it is always fixed. So you can either have 8 bits or 8 digits as an integer. You can have 16 bits as an integer. You can have 32 bits as an integer or 64 bits as an integer because it's an example. It's using base 10 anyway, so it's not even close to what the computer is actually having to deal with, but it's an example. Are we good? All right. So the next question is, what about the Q versus the K row? What are they doing? Okay, so let's just forget about the K versus the S. Okay, the Q is what I call a partial sum when you add two digits in whatever base you're dealing with. So this time we're basically saying 2 plus 9 has a single digit sum of 1. Okay, is that concept okay? So let me ask you a different question. Okay, it's not on the whiteboard. In base 10, what is the single digit sum of 6 plus 7? It's okay, so the actual value is 13, but if I need to only access the single digit sum, what would that be? It's the 3, okay? It is the 3. In other words, I'm not sure how many of learned arithmetic this way. You probably cannot remember, but I do remember mine. Is when you first learn addition, and you have to deal with the sum being greater than the base, which is 10 for most people, what do you need to do? Okay, so let's just say that we are adding 6 and 7. Okay, so when I was a kid, I was given a block that has 6 units. It's 6 units long. Okay, so when I need to add 7 to it, I pick up a block that is 7 units long and put it side by side. Okay, kind of like this, right? So we have to kind of this one, this is to do like that. Okay, and then we realized that, oh, it's longer than, it's at least 10 units long, which means it cannot be represented by any base 10 digit. Does that part make sense? Because that's also important. Okay, so we look at this and go like, well, it cannot be represented by a single digit in base 10, but if I need to use a multi-digit number to represent it, what is that going to be? So we just count, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We do a little cutoff here, and we say this part, okay, is our single digit sum. It goes to digit 0. The rest, we'll use other digits to deal with it. Does that make sense? Does it match how you learned addition? No. How? uh, Okay. So how did you learn addition? How did you learn multi-digit addition? How does your teacher explain that your 66 plus, 95 is, okay? What is 6 plus 5? You go like it is 11, right? This is our single digit sum. Okay? So now you're left with 6 plus 9, which is 15. The 5 is the single digit sum for digit 1, but you also have to add this 1 to it. So 5 plus 1, which is a 6, but you have a carry over here. And if I limit myself to only 2 digits, then I can say 66 plus 95 is 60 with an overall carry of 100, because that's what this 1 is representing. It is a digit 2 in base 10. Digit 2 in base 10 would be representing the quantities of 100. So are we good so far? All right. So what I have done is really just reformat the way that you normally would do your hand, addition. So the carry has its own role. That's all. But the math is pretty much the same. Are we doing okay so far with the example of 1.1.1? Because that is important, okay? Because this is defining the structure of how we perform multi-digit addition in any base. We are just using base 10 as an example because we are familiar with base 10. Are we good so far? Yes. So K is carry, but I cannot use C because I'm reserving the symbol C for something else. I cannot even remember why I chose Q. X and Y are just the numbers being added. Yep. S is sum. Yep. They are all kind of defined, in the notes. Yep. So are we good so far? All right. So now that we know, how your base 10 addition is restructured to look like this, okay? So now what we need to do is to figure out the relationship between the digits. But in order to talk about the relationship between the digits, we need to give them names, right? Instead of using my mouse pointer all day long to say we are talking about this digit and how it is combined with this digit and how does it relate to this digit, that's not good. Okay, using pronouns in a setting like this is disastrous. It is better to give everything a specific name so that there's no ambiguation. So the general name for this thing, this 2 here, is x0. It is digit 0 of x. I'm just going to randomly pick another digit over here. This 2 over here is y2. It is digit 2 of y. Let's pick this guy over here. Okay, this is q1 because it is digit 1 of q. Let's pick this one over here. This is K3 because it is digit 3 of K. And we'll just pick one more. Okay, I know you guys are getting bored. This is S of 1 because it is digit 1 of S. Is that okay? It's the nomenclature, which is the way we name each and every single digit. Okay, so far. Okay, so once we have those naming convention done, then we are going to extract the pattern. Okay, so the pattern is basically saying, how do the digits relate to each other? So what we'll do is we are defining a few functions first. So we're defining C for carry, and we are assuming that U is a single digit in base 10. We are assuming V is also a single digit in base 10. So that gives me a range constraint already. U can only go from 0 to, okay, parameter U, which is what the mouse pointer is pointing to, is a single digit in base 10. What is the range of value of U? 0 to 9. That is correct. And same thing with V. Okay, so those two constraints are actually important. So what C is going to return is whether the addition of U and V ends up with a carry. Okay, it has an answer of 1 if there's a carry, and if it does not have a carry, it answers with a 0. Is that okay? All right. So now we look at the full equation. Okay, let me point to the end of the formula because it just looks a little bit confusing because of the O, uppercase O of OR. This is the end of the whole formula. Does everybody know how to interpret the question mark and the colon in this expression? Yes, it is a ternary operator. Okay, so now the next question is, does everybody understand what is a ternary operator? Okay, I see a lot of nods. I don't see any knots. We see knots and not knots. Does anyone want to say a knot? Okay, well, I'm not a mind reader, so unless there are people saying not, I would assume that it's a nod. Are we good? Okay, so, well, the answer is this is one way to do it. Okay, you you add the two. Okay, if it is greater than or equal to 10, then you answer with a yes. If it is not greater than or equal to, you answer with a 0. That is how we determine whether the single digit addition of u and v is going to end up with a carry of 1 or carry of 0. Is that okay? All right. So the next one, which is R, okay? So R of UV is defined here. Let me move the mouse pointer so that we can focus on just that definition. So this is the entire thing. This is going to give us the single digit sum of adding two digits in base 10. So, okay, we can plug in some numbers to kind of test it out, right? So let's just say that we are adding 7 and 8. So U is 7, V is 8, okay? What is this going to do? 7 plus 8 is 15. So now we have 15 here. 15 mod 10 is 5, okay? So 5 is the single digit sum of 7 plus 8 in base 10. Does that make sense? Does it match what we just talked about earlier? Yes? Okay, all right, very good. So now we have the C++ implementation of exactly the same thing. Okay, so I'm just defining a C++ function R to do the same thing. We have defined a single digit, we have defined a carry or C function in C++ to do the same thing that we just talked about. Okay, so are we okay so far? Just kind of converting the math equation into C++ code. All right. So now that we have the definition of R and C, we can now define the relationship of the Q, the S, and also the K's. Okay, so now um, hmm, I'm just thinking about how to do this. I think I can kind of do a quick one here. All right, so give me a second here. What I'm trying to do a little trick so I can show a portion of this thing here so that I can show you the example in relation to the definition of Q and C. So we'll show this all the time. And then we get to the definition down here. There we go. We got everything that we need to perform the explanation. So this is saying your Q of I is the R function applied to xi, yi. So first of all, do we have any questions about the notation? Q of I is R of xi, yi. It is the single digit sum of xi, yi, or the xy digit of the same column. Let's double check. Okay, let's double check and see whether that makes any sense. X0 is a 2, Y0 is a 9. 2 plus 9 has a single digit sum of 1. That's why Q0 is a 1. Okay, randomly pick another one. Okay, 7 plus 2, which is digit 2. X2 is a 7. Y2 is also a 2. 7 plus 2 has a single digit sum of 9. And Q of 2 is exactly 9. So are we good so far? That Q of I is the R of XIYI. Yes? No? Maybe? Okay, so I'm assuming it is a yes. So now we look at the case, okay? K0 is usually a 0, okay, because there's nothing to contribute to have a carry of 1 for K0. So K0 is usually a 0, at least for now. But now we have to look at K1, okay, which is this one here. Why do you think K1 is a 1? You can explain it by, oh, it's because of the x plus the y, or it is because of the q plus the k. So which one yields the carry of 1 for k of 1? Yep, x0 plus y0 has a carry of 1. So if you're not convinced, you can plug it back into the equation, right? So you're looking at 2, 9. So plug in 2, 9 back to uv, right? 2 plus 9 is 11. 11 is greater than or equal to 10 is true. So it returns a 1. Okay? But sometimes it is not because of the x plus y. Sometimes it's because of the q plus k. So let's take a look at k of 2, this particular one over here. This one here, okay, let me use a mouse pointer. So this one here is not because of the x plus y, because x1 plus y1 is only 9. It does not have a carry of 1. However, 9 plus 1, the q1 plus the k1, does have a carry of 1. That carry of 1 is why we have k2 being a 1. Is that okay? It is the same kind of addition that you already know. I just write it in a different way. Is that okay? All right. So now that we know that there are two sources to a carry, that's why the equation to compute k of I plus 1 looks a little bit more complex. Okay. So k of I plus 1, and I can be 0 and up. So k of I plus 1 is c of xiyi plus c of qiki. So there are two ways to contribute to a carry of 1 because you can end up with a carry of 1 because you add the x and the y, but you can also get a carry of 1 when you add the q and the k. Are we good so far? So I'm basically rewriting the same kind of addition that you already know, except I just gave every digit a name and I'm defining how the digits relate to each other. Are we still good? All right. So now we look at the sum, okay, which is the last row of the addition. S0 is Q0 plus K0, S1 is Q1 plus K1 and so on. So that's why you can also see the generalization right here. S of I is R of Qi Ki. Okay, does that part make any sense? So we are good? All right. So now that we have extracted the structure of base 10 multi-digit addition, the structure does not change depending on the base. Okay, if you look at the screen right here, okay, let me close the one that is irrelevant. If you look at the screen right here, and I ask you and come up with the rule set for base 2 addition, how would you make changes? What needs to change here? Which part do you think is specific to base 10 and we just have to change that? Yes, exactly. Okay. There are only two places where 10 appears as a part of the functions. Let me point out where. In case you have not seen it, here's one and here's the second one. So if I want to change the system to deal with base 2 addition, all I need to do is to change how R and C are defined. And the only change I need to do is to change the 10, which is the base, to 2, which is the target base that we are trying to work with. What about what about this? What about Qi is R of Xi Si is R of Qi Ki, and K of I plus 1 is C of Xi plus C of Qi Ki. Do I have to change that? The answer is no. The structure stays exactly the same. Okay? So now I'm going to describe a little bit of so this is a meta class, okay? It is a class about a class. It is about how I structure the information or the instruction. I started off with base 10 addition, which most of you, hopefully all of you, feel comfortable with, okay? And then I look at the conventional way of doing base 10 addition and go like, okay, that works, okay? But it's not really giving you the nomenclature. It doesn't give you the structure to name every single digit. If I cannot name the digits, it's kind of hard to express the relationship in general, between the digits. So that's why I came up with the long way of writing a multi-digit base 10 addition, which is this part here. It is basically the same way that you have been doing base 10 multi-digit addition. It just spells out things in a much more, I guess, explicit way. So with that structure, then I name the every single digit. This is x0, this is y1, this is q2, and so on and so forth. So then with that structure, I can finally generalize and say, oh, by the way, this I is really just designating a particular digit. If I is 2, then we are looking at q of 2 being r of x2, y2. Okay, so I generalize the whole thing so that I can now explicitly state how each digit relates to other digits. But that structure really just has to do with how numbers work. It doesn't care about the base. The only place where the base matters is how we define the R function, because in this case we have the mod 10, and also what we compare to, because we are dealing with base 10. But if you're dealing with base 2, we just change the 10s to the 2s, and we're good to go. Are we good so far with the binary, no, excuse me, base 10 addition? All right. So that's the approach. Okay. What I just described is the way that I think. Okay. I start with things that I'm familiar with. I give it a structure. I start to name things so that I can express the relationship between the things. And that's it. Okay. But every single step is a step of abstraction. Can someone tell me what is abstraction? What does that word mean? It's okay. This is not an English class. I'm not going to take any points off if no one can answer the question. Okay, it is a different way, but there's a special we're losing details. Okay, we're losing details that are not important. We're extracting the structure. Okay, but since I am also not an English teacher, I should not be teaching you guys the meaning of abstraction. So instead of doing that, I'm gonna cheat. I'll go to Gemini. Of course, why not? Right? So we just have to ask the question, what does abstraction mean? There we go. It's not that hard. But since I'm using the Pro model, it's going to burn a few bottles of water. It would be worse if I say, please tell me, okay, that please is going to burn another bottle of water. All right, so there we go. At its core, abstraction is the process of removing complex details to focus on the essential features of something. It is a way of simplifying reality or things that we have to do so that we can understand and manage it more easily. So here's my next question. Have you been doing abstraction things, before you come to this class? Because that's what programming is all about. Okay? Programming is all about abstraction. Okay? You know how to do something, you can show somebody how to do something. But can you tell the computer with instructions of how to get that job done? That is abstraction. Okay? All right. Moving on. All right. So we are moving on to base 2 addition. So with base 2 addition, it's kind of cool because with base 10, okay, the difficulty of base 10 numbers is there are 10 digits, 0 to 9, okay? So when you were in elementary school and you have to, now I had to use these blocks to understand, the concept of single digit sum, okay, and also when to use a carry, but there are like, it's a 10 by 10 table. To remember all of that is not that easy, okay? How many people have a younger sibling or a niece or a nephew who is learning how to perform multi-digit addition at this point? Okay, so what do you think is the difficulty of learning base 10 addition? Because you have to remember, you have to memorize. Okay, so 5 plus 7 has a single digit sum of 2. Okay, 6 plus 8 has a single digit sum of what, 4. Okay, 8 plus 8 has a single digit sum of 6. We know it now because we have memorized, but there are many, many cases, right? So let's take a look at base 2, okay, and see what we are going to look at, okay? So let me go back to my editor here because I can just look at, okay, I think this is one case. What do you think is the single digit sum of 0 plus 0? Even without referring back to the R function, what is it? That's 0. What is 0 plus 1? Single digit sum? It's 1. What is 1 plus 0? 1. And then the only one that is a little bit tricky is 1, 1. It is a 0. Okay. Are we sure that we have exhausted all the cases? Because with base 10, we have 100 of these things. With base 2, we only got 4. Are we good so far? What about the C function, right? Same thing. So we now look at C of 0, 0. What is the carry of 0 plus 0? 0. What is 1 adding, oh, sorry, I need to follow the order here. What is adding 0 to 1? Okay, what is the carry in this case? It would be a 0 because 0 plus 1 is just a 1. It does not need a carry of 1. What about adding 1 to 0? What is the carry of 1 plus 0? Is also 0. And then 1 of 1, 1, adding 1 to 1 is the only time you have a carry of 1. And that's it. Okay, but some people will still be saying, well, how is this going to help us? Okay, because how do we get this done in silicon? Okay, because everything that we do in this class, we want to translate it to silicon. We want to translate everything to logic gates, and then from logic gates, we know how to implement in transistors. And transistors are real. Okay, you can actually buy them in onesies. Okay, and you can just kind of put your circuit together. Okay, so we're going to focus on the carry function first. Now, this is only for base 2. Okay, we're talking about base 2 at this point. So if you look at the carry function in base 2, and I look at x, I look at y, I look at the carry of xy, okay? And this time x, y are just single digits, okay? So maybe I should go back to the convention of UV just so that we don't get confused about xy versus UV. So I'm gonna put it back here. It's okay. It's not gonna be a big deal, okay? So we have, uh, uh, okay. Looks like we have seen something like this before. Okay, we have a 0 here, we got a 0 here, we got a 0 here, and we got a 1 here. I vaguely remember we have seen something like this on day 1 of this class. What is it called? Looks like a truth table, right? Okay, so if it is a truth table, what is the operator that can come up with this kind of value? And conjunction. Oh, okay. So let's double check, okay? Let's double check that and say, what if I were to perform just a simple, okay, u ampersand v? 0 and 0 is a 0, 0 and 1 is a 0, 1 and 0 is a 0, and the 1 and 1 is a 1. Cool. This means I don't need to rely on comparison anymore, okay? Because in base 2, the arithmetic version of the C definition would give us exactly the same answer as a logical AND. Are we good? Can we implement logical AND using transistors? Because we can use 3 NAND gates to perform the same thing. Actually, it's only 2. How do we know that we can use 2 NAND gates, NAND gates, to perform a single conjunction? Because that's what you did on last Thursday. Okay, so you have to try to make connections between all the things that we talk about in this class. The more you can make association, the easier it is for you to understand additional concepts. Okay, so that's something I would encourage you guys to do, is to think about, okay, how does this relate to something that I have learned already? Okay, because the more connection you make, the quicker you can learn new concepts. The skill is learned. Okay, nobody was born knowing how to do that. Everybody had to practice in order to perform that kind of um, process. And how do we call that process? Making association of concepts that you have learned already to a new concept that you're trying to learn. What is the verb describing that process? The fancy version of that word is comprehension. The simple version of that term is understanding. Okay? How is understanding different from knowing? Okay? Think about what we say to other people. Okay? It's good knowing you is one way. It's I understand you is the other way. What is the difference? Hmm. If you understand something, you might have a chance of being able to apply that. But if you just know something, you probably cannot apply that concept in a lot of cases. Okay, so understanding is really important. Okay, so in the context of AI, is it worth anything that you know a lot of things? if you go to a job interview these days as a software engineer and you tell the employer and you go like, I know all the programming languages, is that worth anything? It's worth next to nothing. Okay? Why is that? I just illustrated that a little bit earlier. Because the AI, not just the AI, a search engine will out know you any day and be a lot faster. Okay? So knowing stuff is not useful much these days. But understanding is different. Okay? Being able to understand something allows you to, okay, troubleshoot, critical think, and create new things. So that's why understanding is important, and that's why I'm trying to tell you guys, what to do with the things that you're learning. Is not the individual pieces that is important, it's the connection between the pieces that is important. Okay, but from your perspective, it is the skill set that help you make the connections between the pieces that is really important, because that's one thing that you can take out of this class and reapply that every single time you take another class. I don't even care what class you're taking. Okay, the same skill can still be applied and still be useful. All right. So now that we are done with this one, let's work out the other one. Okay, so we got UV. This time we have R of UV, and we don't know what the other side is going to look like, but we are going to spell out the table first. Okay, that's a 0. Oops, that is a 1. That is a 1. And that is a 0. Okay, so what are you going to do this time? For those of you who have read the notes, you know exactly the Boolean expression that can do exactly that. But, we can try to work this out. Yes. Oh, 1, 1 should be. Sorry. Thank you. So this is supposed to be a 1 and a 1. Okay, so what do you think is one way to get the same result? Well, we'll focus on one row at a time, okay? If I want to derive a Boolean expression that is a 1, but only if when u is a 0 and v is a 1, what is that going to look like? Hmm, let me see. If I want that expression to be a 1, but only for this row, it's going to look like, let's negate u first, and then end the whole thing with v. So I'm going to put parentheses just to be sure that we are negating the u first. Does that make sense? This expression is true, but only for the second row. Okay? So now we look at the third row and say, yeah, we also want u to be a 1. What equation or what expression will turn the third row to a 1? In other words, when u is 1 and v is a 0, we want this expression to be a 1, but it should be a 0 for everybody else, for all the other rows. Well, to apply the same trick that we have learned, I think that will do the trick, right? And if you're not convinced that this is going to do the trick, make 2 more columns for the truth table just to see that. Okay. In fact, I will do it. Okay. I will do that. So we'll take this and turn it into its own row, and we're going to take this and turn it into its own row column. Sorry. There we go. All right. So in this case, because v is a 0, that whole thing has to be a 0. And in this case, this is going to be a 1. And in this case, it's going to be a 0. And in this case, it's going to be a 0. And then we work out the third one, the fourth, no, the fifth column. This is going to be a 0. This is going to be a 0. Because when u is a 0, the conjunction is going to be a 0 in this column. This is the time when it is a 1, because u is a 1, v is a 0, but not v is going to be a 1, so we end up with 1 and 1, and this is also going to be a 0. Okay, so with this much worked out, what do you think is the overall expression that will replicate exactly what we need for the R function to work? Just ORing those two expressions that we have just worked out, right? Because if you do a OR of the not U and V, or U and not V, that means if at least one of these two columns is a 1, the result is a 1. So that means the middle two rows would be 1s, but the first and the last row would be 0s. So that's the way to derive this. So now we just say, oh, okay. So we just need to work that out. Okay. I'm too lazy to rewrite the whole thing, even though it might actually be a little bit faster. Let's see. U and not V. That will give us the answer, right? So this will give us a 0 here. It will give us a 1 here, and give us a 1 over here. Oops. And it will give us a 0 here. Okay. What is the big deal? Tack, why are you doing this? Okay, what is the big deal of turning the R function, which involves addition and mod and stuff like that, to something that is Boolean? What is what is the purpose? Well, let me ask you. Can we use can we convert negation to transistors? And how do we know that? Because that's what you did last Thursday. Okay? So even I remember what you did last Thursday. Okay? Okay. We already know the AND can also be turned into NAND gates, which means it can be done with transistors. We didn't do the OR, okay? The OR was not in the lab last Thursday, but I talked about it in the class, okay? I even mentioned De Morgan's law, okay? So that means, even though it looks a little bit ugly, it can be done using transistors. Are we good so far? So if you are realizing in your own mind that, oh, this is great because we just converted something that needed to be done using arithmetic operation, and we now can do all of those things using logic gates and then translate everything to transistors. That is the step, the significant step that we have made. Because the idea is, how do we do all this using transistors? And now we are almost there, okay? And I said almost there because there's a plus that is still troubling us. Let me go back to the notes. So the plus that is still bothering us has to do with this little plus here, okay? In other words, the carry of the row k can come from adding the digits from x and y, but it can also come from adding the digits of q and k. So this plus is still gonna is bothering us because we're trying to define how to perform addition using addition. That's just circular reasoning. It's not gonna get us anywhere. So now we're gonna look at that and ask the question, can both of these be ones? In other words, okay, let me use a truth table. This time it's not exactly a truth table, but it is a table. So the question is, if I look at C of xi, yi, I look at C of qi, ki, I know both of them can be zeros, okay? So now when we look at the addition of these two, C of xi, yi, whoops, plus C of qi, ki. Okay, that's just going to be a 0. We know there are cases where only one of them is a 1, okay? So we can go like, okay, maybe this one is a 1. The result would still be a 1 over here. And this one can be a 1. This one can be a 0. The result would still be a 1 over here. So now the question is, can they both be 1s? Because if they cannot be both be ones, that means the third row or the last row does not matter. It's not going to happen. If it doesn't happen, an OR gate can do this. Does that make sense? Does everybody kind of understand the reasoning? Because if it can happen, then we cannot use an OR gate. Because if this can happen, then the answer to this question is going to be a 2. And if we try to do a little shortcut by using an OR, then it's not going to work. Because if we turn the arithmetic addition to a logical OR, then we have almost the entire solution. Because the first, the second, and the third row will all work out. Unfortunately, the last row is not going to work out because if both CI, and C of QI, can both be ones, then I cannot use disjunction to replace the addition. So now we have a problem. So how can we know that C of XIYI and C of QIKI cannot both be ones? Does everybody understand the question that I'm asking? I'm asking why the last row cannot happen. Okay, so what are you going to do? If this is the question that I give you a whole weekend to work on, what are you going to do? There are a few ways to do it, okay? But you can reason this through, okay? We have actually learned enough material to prove this, like mathematically prove this once and for all, okay? Because in logically it makes sense that they cannot both be ones because it never happens in base 10 addition. In base 10 addition, you always have a carry of 1. When was the last time you have a carry of 2 in a multi-digit addition in base 10? It never happens. Just because you have not observed it happening does not mean that it will not happen. Okay? So now we want to have a rigorous proof that it cannot possibly happen. Okay? Why do you think I'm so okay, I'm gonna say the word anyway. Why do you think I'm so anal about you know the rigor of the logic of what we do? Okay. Is computer science an approximation of something kind of like painting? We just have to get the shape right and it's all good. In fact, if the shape does not is not right, it's worth more money. Just ask Picasso. Is computer science, a subject like that? And instead, what do we need? We need logic, right? We need to know this is not going to happen, this will happen, and so on and so forth. Okay, we need to differentiate between all of those cases. So now the question is, how do we prove this? So we'll start with an assumption. Okay, we'll assume that C of XIYI is a 1. Okay, we'll say assume. Okay, all right. So based on what we have just worked out, so this implies, okay, I'm going to use this symbol to mean implies. So this implies xi is a 1 and yi is a 1. Does that make sense to you? And why does it make sense to you? The reason is actually still on the projector right now because of the truth table. Because if you look at the truth table, the only time C of blah blah and blah blah is a 1 is when both parameters are ones. It cannot happen when at least one of them is a 0. So if I tell you that we assume C of XI, YI is a 1, it automatically implies XI is a 1, YI is also a 1. Does that make sense? Are we good? Okay. So let's go ahead and perform more implications. And this implies Q of I is what? How do we define Q of I? Where's the definition of Q of I? So if you're not writing down because the notes already, my module already has this, you might want to consider copying all the equations somewhere in your notes so that you know how to find it. This is how Q of I is defined. Q of I is R of XIYI, And if both of them are ones, according to this table here, one, the R of 1, 1 is a 0. So we know that Q of I has to be a 0. Is that making sense so far? Okay, all right. And what is that going to buy us? Well, guess what? This is going to buy us the conclusion or half of the conclusion that I really need, because this implies C of Qi Ki has to be what? Remember, in base 2, the C function is a conjunction. It is just a straight up conjunction. So if we know Q of I is a 0, what is the conjunction of 0 and something? It's still in the truth table on the projector, okay? If we know Qi is a 0, it means we are looking at the first two rows over here. The answer has got to be a 0, okay? So now we say, oh, okay, this is great. So that means if C of Xi Yi is a 1, it is guaranteed as a result that C of Qi Ki is a 0, okay? But does it work the other way around? Okay, if I give you and assume that Q of C of Qi Ki is a 1, does that also imply C of Xi Yi is a 1? Okay, we have to work that out. Okay, just because the arrow works in one direction does not mean it goes in the opposite direction. So now we work out, okay, what if I tell you Qi, C of Qi Ki is known to be a 1? What do we know about that? Well, the only time the C function gives you a 1 is both parameters are 1s. Okay, so that means we know right away Qi is a 1, oops, and Ki is a 1. That's just based on the definition of the C function. Okay, but if I know Qi is a 1, what do I know about Xi, Yi? Okay, you look up the function up there a little bit. How do we get the R function to return a 1? Because Qi is R of Xi, Yi. So what do we know about Xi, Yi? Well, we know that Xi can be a 0, but if that is the case, Yi would have to be a 1. This is one case. What about the other case? Or, oops, we also can conclude the other way for the exclusive for R of Xi, Yi to be a 1 is for Xi to be a 1 and Yi to be a 0. Is that okay? Does that follow the definitions and the truth tables that we have talked about so far? Okay, I hope so. Okay, because this is based on really just all the definitions that we have talked about. Okay, all right. So, okay, now what can we possibly do about these two cases? So I'm going to use this format here. In this particular case, what do you think is C of Xi, Yi? If Xi is a 0, Yi is a 1, what is C of Xi, Yi? Has to be a 0 because the C function is a conjunction. Okay, what about the other one? What if Xi is a 1, Yi is a 0? What is the C of that? So C of Xi, Yi in this case is going to be also a 0. Okay, so now I ask you, what is 0 or 0? It's a 0. Okay, so that means this implies uh, C of Xi, Yi is a 0 because it doesn't matter how you make Q of I a 1. In both cases of making Q of I a 1, C of Xi, Yi is guaranteed to be a 0. So now we have the other proof. Okay, we have the other half of the proof. If I tell you C of Qi Ki is a 1 to begin with, we come to the conclusion that C of Xi Yi is guaranteed a 0. So is that enough to convince you that they cannot both be 1s? Cool. All right. Uh, Remind me again why we are doing this. Exactly. We are trying to rule out the last row over here. We're trying to rule out that this row is irrelevant because C of xi yi and C of qi cannot both be ones at the same time. So if the last row disappears, okay, because we just say that, okay, this row is irrelevant to us because it cannot possibly happen because of the way the q of I is defined, we're only left with only three rows to have to deal with. And on these three particular rows, the addition versus the disjunction will give us exactly the same result, which means, oh, we can ditch the last addition and replace it with disjunction. And tell me again why that is significant. Why are we doing this? Why are we replacing the addition with an or? Exactly. So you're both right. Okay. So that we can implement the mechanism not using arithmetic operations, but using logic gates. But all the logic gates, and or not, can be implemented using NAND gates, and NAND gate is just four transistors. Is that okay? But tech, this is useless. I don't see the point. This means we can perform base 2 addition. What if I have a base 10 number? What are we going to do about that? Base conversion. Every base 10 number is representing a value. The same value can also be represented in any base, including base 2. So that means with this mechanism, I can now perform addition of any value, at least integers, okay? At least integers. Are we good so far? And this is a really important part. Now, I haven't really talked about the construct of the logic gates, how everything is stacked, but just based on the relationship between the digits, that gives you a clue of how to construct the circuit using and or not gates. Okay, this is a really important part inside a processor. Okay, at the very core, what do you think a processor can do in order to implement all your fancy C++, functions and programs and JavaScript and whatnot? Okay, but at the very core of a processor, what do you think it can do? It can do addition, it can do subtraction-ish, okay, because those two are actually really related. They can it can quote unquote compare. Again, you give it two numbers, it will tell you whether the first number is less than the second number. That's all the computation it needs to know. Okay. Then what about the fancy stuff that we do? What about the video gaming thing that we do? Okay, the rocket ship, the reflection, and the dispersion of the fog effect and whatnot. What about those fancy stuff? They all boil down to multiplication, division, okay, and also the other fancy functions. If you take, I think it's numerical analysis, or um, is it numerical analysis? They talk about how to implement sine, cosine, tangent, and stuff like that. Maybe. Okay, but they all boil down to addition and subtraction and comparison. Subtraction, okay, comparison is a special form of subtraction. Subtraction is a special form of addition. So that means if we can do addition, that's the only kind of computation we need to know. You guys do not seem to be impressed, or do not seem to be go like, wow, that is kind of cool. But it really is that kind of cool. Okay. And that's why I talk about this. Okay, so now we're constructing larger and larger components inside the processor. Okay, there's one particular major component. It's called the ALU, which stands for the arithmetic and logic unit. Its main job is calculations. Okay, mostly now the fancy stuff you can also do multiplication and division in hardware, but you can do multiplication once you know how to do addition. You can also do division once you know how to do multiplication and comparison. Okay, think about how you do your division. How do you do long division? Okay, it is you. That's why you need to master multiplication first before you can even try to learn how to do division. Especially when your divisor has multiple digits, it gets it gets a lot hairier that way. Okay, but everything boils down to addition. All right, so I'm gonna give you the access code of today's lab, and then we're gonna go to the lab. I cannot remember the it's space conversion for today. I set up the time already. There are only 8 questions, and it basically is based on what we learned a little bit earlier today. And the access code is heptapod, which are basically creatures with 7 limbs. Because we've been talking about base 7 numbers, and people ask, why do we care about base 7? Because there are heptapods, pods in the world. Hepta, which is 7. Pod means limb, so heptapod is 7 limbs. Huh? Yes. Have you watched the movie Arrival? Yep. Or you can think of it as an octopus that has one tentacle holding to a can of beer, which only 7 limbs left for counting. And if you ask, how can an octopus drink beer when it's underwater? All you have to do is to watch SpongeBob. That explains all the physics. Hmm? Fire in the water, drinking in the water. Yep, SpongeBob.